In order to determine whether a variable, an independent variable, is a good predictor of a dependent variable, or to determine whether it is useful to add a variability in the slope or in an intercept, in multi-level modeling we use the model comparison approach. So let's first consider the components of the models that we are going to compare. Basically, we are going to use linear models, and linear models have a slope and an intercept, and both the slope and the intercept of the intercept and the slope of any independent variable or predictor variable could be fixed or a random component. So I repeat, for the slope of the linear model corresponding to each of the independent or predictor variables, that slope could be either fixed or random. And for the intercept of the linear model, that intercept could be fixed or random. Okay, what is it fixed and what is it random? A fixed component is a component in which the variability for that component is not calculated. And a random component is a component for which the variability is calculated. So I'm going to show you the examples of models combining these possibilities. So some of the models are typically used, and sometimes some models are less used. Some models I have a particular interest because we can compare this multi-level modeling approach with the traditional approaches. So the model 00 is a model with a fixed intercept and no slope. So basically there are no independent variables, or the independent variables are not considered in this model. And for the intercept, well, it is fixed, so we are not going to consider the variability. So basically this is equivalent to estimating the mean of the dependent variable. A second model, well let's call it 0, has a random intercept but no slope. Again, because there is no slope at all, it means that we don't consider at all the independent or predictor variables. So, but because we have a random intercept, so basically we are calculating the variability of the intercept. And what does it mean that we calculate the variability of the intercept? It means that we assume that the data is going to be fit better if we consider that for each instance of a level 2 component, we need to calculate an intercept. So basically this would be like if we have 4 schools, and this is equivalent to calculating the mean of each of the schools and comparing them to the total mean. So this is a one-way ANOVA. The model 1 is the one that is more interesting from the perspective of multi-levels, is the fixed intercept and fixed slope. In fact, this is a null model because it doesn't have any random component. Now, this is equivalent to the traditional linear model, in which we've got one independent or predictor variable and we calculate its slope, and we've got the intercept. Model 2 has a random intercept and fixed slope. So basically in this case we consider that it's useful to calculate the variability of the intercept, but not of the slope. So in this case, we consider that it's useful to have one intercept per school, but the relationship between the independent variable and the dependent variable is the same for all the schools. They just have a different intercept. Model 3 has random intercept and random slope. So one thing that is important to consider is that the colors of the intercepts, the colors of the slopes that or of the lines of the regression have some meaning. So basically the one in red is more likely, and the one in dark pink is less likely, and the one in light pink is even less likely. So it is not exactly the same as comparing as calculating a slope for each group, because that would be calculating too many parameters. So what we are doing is to calculate a variability of the intercept, or in this case the slope, from the mean. So that means that slopes or intercepts that are far away from the mean slope or the mean intercept are less likely. And that what in effect causes is what we call a shrinkage. So the supposed slopes or intercepts are closer to the mean than if we calculate the slopes and intercepts on their own. Okay, so in here I'm showing the case of the intercept is random. So we've got 5 lines that intercept the value of 0 of x in the y-axis at different levels of the y-axis. So that's a random intercept. And then we've got different slopes. And in this case, the type of dash I use in the lines indicate which ones are more likely. So slopes that are further away than the mean are less likely than the ones that are close to the mean. And in this case, I only showed 2, so variability in the slope of 2 of the 5 lines, but you can imagine that you should have all the lines should have those possibilities. Just for it would be messy to show all of them. And the model 4 is a fixed intercept and a random slope. So basically, in this one, we consider that all the schools have the same intercept. So basically, that they have the same mean in the dependent variable, but the relationship between the independent variable and the dependent variable varies among the schools. Now, when we fit the data to the different models, we are going to obtain measures of goodness of fit. And these are the main measures that are used. One is the log likelihood. And the log likelihood is obtained as follows. For each observation, we calculate the probability of observing that value for the model. So remember that in linear models, we always use a normal distribution or some other distribution, sometimes a t-distribution, to predict the data. So each observation is predicted with some distribution. So in that distribution there is a probability of observing that value that we observed. Okay, so we've got for each, when we create a model, we got for each of the observations one probability associated to it. So now we want to know what's the probability for the whole model. Well, what we need to do following probability theory is to multiply all the individual probabilities. Now, remember, probabilities are values between 0 and 1. So multiplying values that are lower than 1, they become lower and lower values. So if we have a very large sample and we start multiplying all these values, we are going to have very small values. So in order to avoid that, what we can do is to calculate the logarithm of the probabilities. And by doing that, we are going to have negative numbers, but they are more manageable than very small values. So what do we do? So now we have for each of the observations one probability, but then we obtain the logarithm, so we get what is called a log likelihood for each of these observations. And what do we do? So in the case of probabilities, we multiplied all the probabilities, and in order to obtain the total probability for the model. How do we do with likelihoods? Do we multiply them? No, we actually have to sum them. And when we sum them, we obtain the log likelihood. And if we exponentiate the log likelihood, we obtain the probability of the whole data. But we don't do that. We just keep working with the log likelihood because it is much more manageable than the total probability, which is a very low number. Okay, so now the log likelihood is a negative number, and the more negative the number, the worse the model. Think about it this way. So if your probabilities are very high, when you obtain the logarithm of those probabilities, it will be a negative number, but close to 0, not a very large negative number. So the more negative the number it is, the less probable the observations are. Now it's uncomfortable again to deal with negative numbers, so then we calculate the deviance. And in order to calculate the deviance, we just multiply the log likelihood by -2 or -2. What it does, it transforms the negative number into a positive number because we are multiplying two negative numbers, and then it doubles in value. So now the larger the deviance, the worse the model. And that makes sense as well, because the deviance is telling us how large is the deviation of the prediction of the model and the actual observation. So the larger the deviation, the worse the model. And remember that we need to penalize for having extra parameters, because in order to avoid overfitting, we don't want models with a lot of parameters. So the BIC and the AIC are statistics that penalize for adding extra parameters. So they use different formulas to penalize, and they both start with the deviance, and then they add some penalty for every extra parameter that is estimated in the model. Now, AIC stands for Archaic Information Criterion, and BIC for Bayesian Information Criterion, and there is a relationship between the Bayesian Information Criterion and the Bayes factor. So, but I'm not going to explain this in here. Now, so when we obtain, let's say, just the BIC, so BIC and AIC are equivalent in what they try to do. They are a measure of how good the model is, and they incorporate penalization for adding extra parameters. But let's continue with BIC. Remember, deviance, the larger the value, the worse the model is. BIC is the same. It will start with the deviance and it will add points for extra parameters. So if you have extra parameters, you're going to have a larger value. Now, when we compare models, we are going to obtain a BIC for each of the models. And then we just need to see which value is larger or smaller. And the smaller the BIC, the better the model. So we're always in model comparison, the comparisons are relative. So a model will be better or worse than another model. Always a relative comparison. It's not an absolute measure. So the value of BIC that we obtain doesn't mean anything. We just need to compare with another model. That's why I always talk about null models that are important, because we need to compare to those models to determine whether our model is good or not.